All right, this is amazing. It's amazing when it works. Okay, so like I said, we're going to talk about building adaptive systems. Um, so this was our world when we were at Bleach Report. We had servers talking to other servers, and they needed to send communication back and forth. This was the context by which we did just about everything. And these could be RPCs, they might be Gen server calls, they might be talking to a database. It doesn't matter what the thing is, right, that you're talking to, but this is hopefully emblematic of a lot of our work. We have servers talking to other servers, and they're running some process and doing some sort of work. And what happens is one of those servers says, I have a request, and it sends that request on to the other server. Assuming that server has nothing else going on at the moment, it often just says, okay, sounds good, not a problem, finishes up doing whatever work it needs to do, serving a request, saving data, reading from a cache, whatever that may be, returns the response back to the original, to server A here. Server A says thanks and goes about its day. And this is great. This is how we like to view the world. But as anyone here probably understands, and as lots of people will tell you if they've worked on large scale systems, this isn't your reality most of the time. And in fact, this is the least interesting part of your job, because this just works and you don't have to think about it. Most of the time, things don't work at all. Most of the time, things are failing constantly. And it's sort of a known quantity that any system of sufficient size is running in degraded mode basically at all time. That's just a truism. And I'm here to say my empirical evidence supports that. So what ends up happening is you say, hey, I have a request. That server sends over the request, and the downstream server says, I'm busy. I've got other stuff going on. I'm garbage collecting, or the database started backing up, or whatever it is. For whatever reason, I'm backed up. But the upstream server doesn't know that. It doesn't care, because at the end of the day, all the requests coming in are probably from your users. In queuing theory terms, we would say this is an unbounded queue. And you've got a whole bunch of people sending you requests that they want satisfied. They want to see latest news about whatever, somebody getting traded to some other team or what have you. So the upstream server says, just keep sending requests. And it keeps doing this over and over and over again until eventually it builds up this queue. And the server downstream, having all this extra load on it and all this other stuff going on inside of it, using up all these other system resources, eventually just says, I can't handle this anymore, and it goes away. So if that was the end of the story, that would be bad, but it actually gets worse, because even after that downstream thing is gone, those unbounded requests that started up at the top of your queue, at the top of that first server, are still coming in, and now they're queuing up in front of that server. They don't care that the downstream thing's gone. There's no back pressure here to speak of, right? Because you don't control all these clients. You don't control users coming to your site. So now all their requests start backing up. And when that happens, that server gives up too, and it starts going away. This leads to what we all sort of refer to as the sort of cascading failure problem, right? We've all seen these sorts of things happen in large scale systems, and it's why we talk about, when we talk about resiliency, this is in a lot of ways what it is that we're talking about. This is at the core of a lot of those resiliency problems. And this is, like I say, the kind of stuff that we are dealing with at Bleach Report. So how do you go about fixing this? The first thing is to realize that all services, regardless of scale, number of users, data requirements, they all have objectives. And by objectives, I mean, they all have stated goals. Well, they may not always be stated. And in fact, often they aren't stated, especially when you're early in your life cycle as a system. But they all do. Often they're all implicit. And it may be things like, we want to serve 100 good, where good means fully satisfied, fully realized, up-to-date, most up-to-date liveness requests. We want to serve that per second. And that may be your goal. Your goal may be 10,000 of those. Your goal may be 5 of those, right? You don't know, but you have some sort of goal. And it's up to you to determine those in your business. I will posit to you, though, that A resilient service, a service that can withstand load, right, and withstand failure, should be able to withstand a 10x traffic spike and continue to meet its objectives. Now, I want to break this down a little bit because that may be overwhelming. When I say it can receive a 10x traffic spike and continue to meet its objectives, I don't mean that if your goal is 100 requests, good requests a second, and you get 10x of that, so 1,000 requests a second, that you serve all 1,000 requests to their fullest extent. What I mean is you meet your goals. Your goal was 100 requests a second. So you should still be serving 100 requests a second. What you do with those other 900 requests, that is where all of the interesting problems of resiliency and building large scale systems lies, in my mind. And what we do with those 900 other requests is, well, that's where all the interesting stuff is. So in order to do this, in order to build this and in order to do this at Bleacher Report, these are the things that we went through. So what we're going to talk about today are queues. We're going to talk about overload mitigation. We're talking about adaptive concurrency and how it can be used to support this kind of stuff. All right, so queues. If we buy the statement that I made earlier that a lot of resiliency and being able to support and rather mitigate cascading failure is being able to combat overload, well, then it behooves us to understand what causes overload in the first place. Luckily, and I didn't warn people up front, but I'll warn you now, there will be math in this. Luckily, there is very little easy math. It's not bad. And we'll try to demonstrate exactly what causes overload and explain the math ahead of time. So in your system, you have queues. And in fact, it's basically queues, as they say, all the way down. You can model all of your systems from top to bottom as queues. And the cool thing is there are some global sort of unifying principles about queues that allow that all to play really well together and become this, like, allows you to reason about this stuff without having to get too deep. And that's what makes the math a little bit easier. But when a server gets overloaded, what's happening is that requests are starting to build up in a queue and they're starting to take up resources. So we can kind of denote a few of these things in terms of the queue semantics as both arrival rate and processing time. Processing time is the amount of time that's being spent in, let's say, the server or process or beam process, right? Run queue scheduler, doesn't matter, right? Unit of work, right? The amount of time that's being spent in the thing is what we'll refer to as the processing time. I will also probably slip up and use work time accidentally, and the terms are somewhat interchangeable. And the amount of things that are showing up into your queue, we're going to refer to as the arrival rate. So the amount of things that are coming in is the rate of arrival. So you might have 10 requests a second, 5 requests a second. Those are rates, and we have some number of those. Overload's really simple. If arrival rate is greater than processing time, you have an overloaded queue. And on a long enough timeline, it will continue to become more and more and more overloaded. Hopefully that makes intuitive sense, right? If you have more things coming in, then you can process them, then the queue is just going to continue to grow. There's another law that we can talk about, and it's called Little's Law. It is brought up a lot in queuing theory, so much that it's a little bit of a meme. It's like a little bit like saying CAP theorem around distributed systems people. It has a lot of connotations, but people bring it up because, one, it's really easy to understand, and two, it's a little bit like E equals MC squared. Like, once you understand it, it sort of changes your entire worldview. It has this sort of like large unifying field theory kind of thing going on with it. So Little's Law simply states that the elements in a queue is equal to the average arrival rate multiplied by the average processing time. And on a long enough timeline, that will always be true. And there's a proof for that if you don't believe me, but I think we can try to make some intuitive sense out of this. So let's say, for instance, that your server takes 100 milliseconds to process any given thing, and you have 10 requests a second. How many things are being worked at any given time? Well, we can intuitively know that one thing shows up, it's processed in 100 milliseconds, and then it leaves just as soon as the next thing is arriving. because you have 10 things coming in per second, 100 milliseconds, that works out to be 1 request per second. Hopefully that makes some intuitive sense. So what happens if all of a sudden we increase the work time to 200 milliseconds? We just double it. Well, now we have 2 requests sitting in the queue on average at any given slice of time. So if we look at a long enough time window, we can just say like, okay, well, on average, there's going to be 2 things just sitting here. And that again makes intuitive sense. You've got stuff coming in, takes a little bit longer to process, and now you've got stuff starting to build up. So that math is pretty straight ahead, but it gets slightly more complicated when you start to think about what is actually happening under the hood when these queues start to build up. I mean, 2 things isn't that big a deal. These are beam processes. They aren't giant things. They each take like what, like a K, like a gen server is like a K of memory if you have no state in it. You know what I mean? It's like, it's not a lot to consume. But as you add processes, all those processes need to be scheduled. The more memory you do have in those processes, the more garbage collections you're going to like kick off. So the more memory you're starting to use up, the worse your CPU is going to do in general under real high load, because now your beam has to garbage collect a lot more often. It's got to reschedule all that stuff, which means you're fighting like getting stuff rescheduled back into the queues over and over and over again. So all this amounts to more CPU pressure. What happens when that happens? Well, your latencies start to increase. Your work times start to go up because now you're starving the system of resources. This is a contrived example. This doesn't happen with 2 things, right? But it does happen when you start to build up thousands of things all at once. Which, if that seems like a thing that probably doesn't happen that often, I'm here to tell you that was the problem we were dealing with. Like, we had thousands of things all happen literally all at once, and we were trying to figure out how to combat that. So all of a sudden your requests start to build up, your latencies go up, your requests, the number of things in the queue start to increase, and you exacerbate the problem over and over again until it finally jumps to 3 seconds, and then eventually goes to infinity. And then as it goes to infinity, it's been a while since I did calculus, but I'm pretty sure that's infinity. And so you end up with a system that's overloaded. And it's cool. Little's law is really useful for this. I've literally sat and debugged production issues with Little's law and been able to start to pinpoint certain things. It is a really, really useful tool to internalize if you are interested in this kind of thing and if this is the kind of work you're doing. Yeah, and this is bad. So that's queues. That's a little bit of queuing theory. Now let's talk about how we mitigate this. So as we said before, overload happens when your arrival rate is greater than your processing time. Technically speaking, any queue is overloaded when this happens. It so happens that a lot of our queues and a lot of the ways we build our systems happen in real bursty sort of batches like this, and we end up equalizing on a long enough timeline. Overload matters more under sustained load, obviously, and how you're processing that work. But in this case, what we're talking about is sustained load, and we're talking about critical path kind of things. So as we said, arrival rate is greater than processing time. That's bad. In order to control this stuff, we have to get both of these variables under our control. If you only control one of them, you don't control enough of the equation to be able to fully satisfy this problem. So you have to control both these things. So I will now posit to you that the only actual way to solve this is load shedding. And by load shedding, what I really mean is dropping your work time to something close to 0 in a lot of cases. So which happens to reduce, I mean, that's effectively what you're doing, right? You're effectively controlling both sides of it, and you're saying, well, this side of it, work time, we're just going to drop to as low as possible. So what we need to do is start evicting stuff from the queue. If we can't process everything in the queue, we just have to get rid of stuff. There is no other mitigation to this. And I keep saying that over and over again, because it's a thing that people don't like when you tell them this the first time. It doesn't feel good to say, we're not going to satisfy all the requests. And it's really not fun to explain this to your business people or your product people the very first time you go through this. the way you win this, by the way, side note, the way you win this argument with your product person is you say, do you want everything to fail or do you want some things to fail? And do you want to control how we fail, or do you want to let, be thrown about the winds of chance? And that's the way you have this conversation. So we have to evict stuff. We have to get stuff out of the queue faster. That's the only way to start solving this problem. And we have to do it in two ways. The first is the downstream server needs to just drop requests immediately. It needs to just start saying, I am unhealthy. I can no longer handle work. I will not service anything else. And I'm going to now drop you. And it needs to start shedding load that way. That could be good enough, except it means that the upstream thing is still doing useless work because it's sitting there potentially opening a TCP connection, potentially sending this like giant HTTP thing, doing encoding that it doesn't need to do like wasting system resources, sitting there waiting to do things when it doesn't need to do it. And so in order to fully mitigate this problem, we also are going to stop sending requests from the upstream service. Some people, when I approach them, talk about to try to solve this problem, they want to find other ways that don't look like dropping requests. And one of the first ones that comes up is auto scaling. And the thing is auto scaling is a non-solution to this. Auto scaling specifically is a cost savings measure only. It does nothing for your resiliency at all. And don't let anybody tell you differently, because auto scaling does not have enough information to actually build resiliency for you. There's no Kubernetes in the world that is going to actually like make your service resilient. I'm sorry, it's not a real thing. You have to be in control of that. Or you get a bunch of DevOps engineers to build you an Istio and then make them responsible for it. But we'd ideally not like to do that. So let's look at why auto scaling specifically is not useful for this problem. So let's say we have server A talking to server B, which talks to a database. And in this case, the database is under load. Maybe it's Postgres and we're vacuuming, or maybe like someone else is running a reporting query or they weren't supposed to, who knows, right? But for whatever reason, the database is causing us issues. Well, that will manifest as requests queuing in server B, in the middle server there, because it's waiting for now slow running queries. More requests are piling up here. That causes CPU pressure. It causes memory pressure as more requests are sitting there waiting to be fulfilled. And if we were to let our autoscaler look at such naive signals as CPU and memory, which is typically what people are using, well, then what it's going to do is decide that the right course of action is to add more workers and continue to overload the database more. It's like now the Postgres, which can only handle about, from what I can gather with Postgres, about 10 physical connections, now has more. And you've, like, again, exacerbated the problem. And now all you've done is allow more requests to pile up and fail, and probably increased your AWS bill, and a bunch of other negative things. So this is a non-solution for us. All that to say, auto scaling needs to be in response to load shedding. Your auto scaling has to happen after the fact, right? You have to have load shedding in place. You have to have mitigation in place before you can even talk about a real successful auto scaling strategy. Unless, and I would say that's specific for us in Elixir. We have a really good runtime. We have very good, for the most part, like our libraries are pretty, the real battle tested stuff that we use on a day-to-day basis is pretty good about its utilization and queuing stuff. If you're in different runtimes, that calculus changes a little bit, where really truly your workers, like your single-threaded runtime, really is the bottleneck. But in our case, it's almost never the right solution. Another non-solution to this problem is circuit breakers. And I say that we use circuit breakers. I like circuit breakers. This is not shade against circuit breakers. We use those for a long time. But these are a non-solution because a circuit breaker shuts off all of your traffic. If a downstream thing starts having problems, starts having a certain amount of failures, we shut off everything. Well, that's often not actually what we want. And it's counterintuitive to our stated thing up front, which is that our service has objectives. It has goals it wants to meet. It has 100 requests a second that we want to try to fulfill. It's often not the case that a downstream is completely down. It may be having a performance regression, it may be having another problem, but it's often likely that it can serve some amount of traffic. And we want to get as close to our objective as possible. Circuit breakers don't really allow you to do that in a granular way. It also so happens that they are often they're often statically configured, and statically configured stuff for me is not something I'm all that interested in as a robust solution for my first line of defense for resilience. And the reason is because the system's changing too much. Like the underlying thing is changing and adapting and living and breathing too much, and adapting to its own downstream failures, and auto like scaling out, scaling in, building up newer boxes, and I can't control the constellation of services and how those people and what those teams are opting to do with their services, right? So anything that's statically configured can work if you're working with a very small team, very confined, maybe one app or two apps that you can really control. It stops working at about that. That's about where that breaks down, and you really need something more dynamic that can listen to the system and adapt to the system health itself. So circuit breakers are really your last line of defense. You do want them, but you want them sort of around all the rest of this stuff and say, like, if we need to push the big red button, this is the big red button. So that's how we're going to do overload mitigation. We can talk a little bit about the solution we opted to use and build at Bleacher Report, which is adaptive concurrency. So as I said, we want to allow as many requests as we actually can. We want to allow as many requests as we can handle. And we don't want to, and that's what we want to target. Again, we have our goals. We built our services to achieve those goals. Now we want to let them achieve those goals. None of the stuff that we're using is novel, because nothing's novel. And as it turns out, basically all of the good research happened in the 80s and 90s. And we're just riding on the back of that. So all this stuff goes back to the birth of the internet. Which is, and it specifically, I think this is sort of the paper of that, which is congestion avoidance and control. And it describes a way to mitigate congestion in network routers and the rest of the internet. So the way this works is that every service you have has some sort of concurrency limit. The concurrency limit in question is like the number of things it can do at the same time. Right. So you might say it's the number of requests that this service can handle simultaneously, right? Or like the number of things that can be queued inside of it before it starts to become overloaded, right? Before the arrival rate starts to exceed the processing time. And we have some actual limit. That limit for a given service may be known, or at least projected, but how that limit changes depending on how many other workers you have, how big the database is somebody running a reporting query, whatever, is highly flexible. That's not a thing that we can always know. That's a thing that changes literally minute by minute. And so what we're going to do is we're going to build a system to dynamically discover where that limit is. And the way it does that is we're going to increase this line back and forth, and it's going to sort of whipsaw around the actual limit, rising up above the limit until we reach overload, and then dropping back down really fast over and over again to try to discover where the actual limit is under the hood. The way that works in practice is when this upstream thing calls into the downstream thing, it's going to say, hey, are we at the limit for this downstream? And if it's not, it's going to send something else, send a request over rather. And when the upstream service sees that request, it's going to say, hey, can I actually handle this, or am I at my limit? And if it is, it'll satisfy it. And if not, it's going to drop that request. As it does this on both sides of the equation without coordination, without talking to each other, what we're going to do is we're going to measure how long those requests take, how many errors are taking place, and other little key metrics about the system. And we're going to update the limits. And we're going to say, and that happens about periodically. It happens about every 5 seconds. As it refreshes and figures out, actually our limit is 30 now. Actually our limit's 200 now. Actually our limits are 5 now, or whatever. And it's going to grow and shrink that based on measurements that it's taking of each request. So for instance, if all of a sudden we had some limit dramatically decrease because, for instance, a new version of the code went out and we introduced a performance regression, or somebody introduced a new query that forgot to use some sort of index. We'll start to see that. The system will adapt dynamically and begin to start shedding load and starting to allow certain amounts of traffic through based on our goal. Specifically, what we use is we use latency and we use successful versus failed requests to determine on either side. We used different algorithms, I guess you'd say, to determine that, depending on if you were a server or a client. We're going to talk about the client one because the math is easier. But effectively, it did the thing that your router does, or well, it used to do. I mean, this is like from that paper, and it's additive increase, multiplicative decrease. And the way that we calculate the limit is we say effectively what we say is for every successful request, we increment the limit by 1. And if we're in a back off state, for instance, we start to detect errors or we start to detect increase in latency, we start to multiply the limit by 95%. And we start to say, like, actually just give us 95% of this over and over and over again. And it drops off really rapidly and it creates this sawtooth graph over the actual limit back and forth. In practice, it doesn't actually increment per request. It does it in batches because it's faster for the beam to do that because the former would require more mutable state to be fast and efficient. We don't like that. So we optimize it for a slightly different pattern and we just increase it by a fixed amount, but it amounts to the same thing. So we are not the only ones to solve this. A bunch of other people have solved similar problems to this. These are a bunch of libraries that we also used at some point in time, depending on, and there's others in here. Jobs is one in here that I don't have on the list, but Jobs is really good as well. Jobs is probably the most like Swiss Army knife of all of these. You can really bend Jobs into whatever problem you want to solve. But for our purposes, and because we had a very specific problem that we were trying to solve, I built an implementation of adaptive concurrency called Regulator. The only thing that we're really providing that a lot of these other libraries don't provide is we have an implementation of Netflix's algorithm effectively that they use for load shedding and adaptive concurrency, which I developed. Like, I don't know how to say this without it becoming like name droppy. I have friends at Netflix and I talk to them about what they did and I built an implementation of their open source Java thing, but in Elixir. And it turned out to be really, really effective for servers specifically, for helping keep servers alive. On the clients, we tended to use additive increase, multiplicative decrease, because it adapts faster to change and it looks for errors and stuff like that. But in any case, we built this partially because it was a thing that we understood. It was a thing that we didn't need to tune. It was perfectly fit for our use case, which is always a good reason to build something. And setting it up was really simple, which was another key thing. Like, I didn't want to ask a bunch of people managing services how to set this all up. I just needed to say, like, here's how you do it. And how you do it's pretty simple. You just say install, you give it a name, which is an atom, and you tell it what kind of limit you want to use. And then, yeah, when you want to actually call it, you say regulator.ask, you pass it a function, and you can do whatever work you want to inside of that thing. And it does, and it either will or it'll return you dropped. It'll say, like, nope, you're out of your limit. So I'm not going to do this work at all. So yeah, so that is the whirlwind tour of all this stuff. Important things to take away from this. Number one is that queues are really everywhere in your system, and they're in the beam explicitly. We have multiple of them. But you can also think about them in every Gen server. Every process that you have forms some sort of queue. All of your pools are really just queues, right? They're things sitting there waiting for a worker. And the network itself, right, is part of that queue and part of that infrastructure. And if you want to do this kind of work, internalizing that, understanding that sort of implicitly is really, really important. Those queues have to be bounded. And this is something that I think is really important for Elixir people specifically, because we deal with so much concurrency and parallelism. I see way too many people building systems with queues that they don't put any bounds on. And that is a recipe for ending up with a very bad day. That, you know, you're like, you should not do that. So like, put a limit on, even if it's static, you know, you just pick a limit, talk to your people and say, if there's more than 1,000 of these, we're not going to do it anymore, because otherwise your alternative is your system's going to crash. And they say you can't, you know, say it's hard to crash the beam. I've crashed the beam. Like, it's, you know, you starve the beam of enough CPU, you'll bring the beam down. So, you know, it is a real thing that can happen, and it's worth just, you know, thinking through. If your system is dynamic, your solution to the problem will also need to be dynamic. If your system is changing, expanding, you're adding more dynos, you're adding more workers, and you're adding new databases and all that sort of stuff, then whatever solution you come up with to this problem, which you will have, has to also be dynamic. And you have to be able to allow that to grow and adapt to the system that is underlying it. So, and finally, I'll just say, and this is something I always say, but I think it's important to always remember it, which is go out and build awesome stuff. Don't let anybody tell you that you can't build anything. Don't let anybody tell you that you shouldn't have built anything. Go build cool libraries, share them with people, try new, interesting stuff. This is a real fertile time to be in the community, because I still claim that all the best practices, quote unquote, are not cemented yet. And all the cool ideas have not been found yet. So go and find them. Yeah, thank you.